Analysis of symmetrical faults. So, how to analyze a power system network after the occurrence of a symmetrical fault on it. So, analyzing a system means, or analyzing a fault means, to calculate the current through different components as well as the voltage across different points or the voltage across different components of the power system network after the occurrence of a symmetrical fault. So let us see how to analyze symmetrical faults. And we know that the various symmetrical faults or three-phase faults are triple line to ground and triple line to ground. Short circuit between all the three lines and short circuit between the lines, all the three lines and the ground. So we know that they are the most severe fault as well as their frequency of occurrence is very low. They are the least frequently occurring fault and they are the most severe faults in the power system network. And the analysis of symmetrical faults includes the determination of voltage at any point on the network and current in any branch of the power system or current through any component of the power system, and also the determination of the value of reactance necessary to limit the current to any desired value. So if triple line or triple line to ground fault occurs, they are short circuit faults and there will be an increase in current. So we have to reduce that current for the safety of the power system network. So we should also be able to calculate the value of current limiting reactors to limit the current to any desired value. And these calculations helps in the design of suitable circuit breakers and design of protective schemes. So if we are able to calculate the current in any of the branches after the occurrence of fault, we should know how to design the circuit breakers. When we can decide when these circuit breakers should break the circuit and what will be the rating of that circuit breakers. So after calculating the fault currents, we will be able to design suitable circuit breakers and a suitable protective scheme. So various assumptions for analyzing the symmetrical faults are given here, and we are actually solving the symmetrical faults using the reactance diagram. So we have already studied the reactance diagram and we will use the reactance diagram for the power system network for solving the symmetrical faults. So these assumptions 1, 2, 3 and 4, these 4 points corresponds to the assumptions that we have already considered for drawing the reactance diagram. So the same points are given here. Load currents are negligible compared to fault currents. So while calculating the fault current or while doing fault analysis, we will not consider the load currents. And while drawing a transformer model, we will omit the shunt elements. That magnetizing branch of the transformer will be omitted. Only the series reactance of the transformer will be considered. And for transmission lines, the shunt capacitance. When transmission lines are being represented in the pi form, there are two shunt capacitances and they will be neglected. And all the system resistances are neglected and only inductive reactances are considered. So all these points are the points or assumptions that we have used for drawing the reactance diagram. And the last one, see the last one. The EMF of all the generators are assumed to be equal to 1 angle 0 per unit. So generated voltage of all the generators are 1 angle 0 per unit. So we know in a reactance diagram, we will represent the generator as a voltage source in series with a reactance. So that voltage source is given a value 1 angle 0. So EMF of the generators are always assumed to be equal to 1 angle 0 per unit. This means that the system voltage is at its nominal value and the system is operating under no load condition during fault. So a generator is having a voltage of 1 angle 0 means the system is at its nominal value. If a quantity is having a per unit value 1, that means We are calculating per unit as actual value by base value or actual value by rated value. So that quantity equals to 1 means actual value and rated value are the same, or the generator is operating at its rated value or nominal value. And also the system is under no load condition during fault. So we will assume that the system is under no load condition during fault. So these are the various assumptions. So now moving on to the steps in fault calculation. Here also all these steps corresponds to the steps used for drawing the reactance diagram. So we have done problems on per unit computation in module 1, problems for drawing reactance diagram. If the single line diagram of a power system network is given, we were asked to draw the reactance diagram by converting the per unit values of all the components into a common base. So we know that. So all these steps corresponds to what we have done in that problem. Okay. First of all, draw the single line diagram of the complete system. Thereafter, choose a base kV and a base MVA and convert all the reactants into per unit based on the chosen base value. Okay. So already the per unit values of components will be given, and we have to convert the per unit values into a new base which is chosen for the entire system. And thereafter draw the reactance diagram with all the reactances marked in per unit. So this much until step number 3 corresponds to what we have done in the per unit computation problems. And see the step number 4. After drawing the reactance diagram, reduce the reactance diagram and find the Thevenin equivalent reactance of the system as seen from the fault point. So we have our power system network and there will be a fault, a symmetrical fault on any part of the power system network. So from that particular point, we need to find the equivalent reactance of the system. So we have the reactance diagram, and in that reactance diagram, there will be a fault on any part of the system. So from that particular part, reduce the reactance diagram. Find the Thevenin equivalent reactance as seen from the fault point. With respect to the fault point, find the Thevenin equivalent reactance of the system. So after getting the Thevenin equivalent reactance, determine the fault current. So fault current is equal to voltage by reactance. So voltage, we know that we will always consider it as 1 angle 0. So we have seen it in the assumptions. EMF of generators are always assumed as 1 angle 0. So usually the pre-fault voltage at the fault point is considered as 1 angle 0. There are other conditions also which we can see while solving problems. So voltage at the fault point divided by the reactance, the Thevenin equivalent reactance will give the fault current. And also calculate the fault MVA. Apparent power. Fault MVA is the apparent power flowing to the fault point. It can be calculated as voltage into current. Fault current into voltage at the fault point. And after calculating the per unit values of fault current and fault MVA, convert them into actual values. Calculate their actual values. And thereafter find out the current and voltage at all the parts of the network, at every part of the network. These are the various steps in symmetrical fault calculation. Now, so we have seen this point, fault MVA here. So let us see what is fault MVA. What exactly is fault MVA? Fault MVA is also known as short circuit MVA, short circuit capacity or fault level. So fault MVA, fault level, short circuit capacity or short circuit MVA, all are the same. And MVA means MVA is the apparent power, we know. And a short circuit MVA is the apparent power which would flow through the circuit towards the fault point. So it is the apparent power flowing through the circuit towards the fault point. And it is defined as the product of pre-fault bus voltage and post-fault current. Short circuit MVA at a bus. That means if a short circuit occurs on a bus, The apparent power flowing to that short circuit point is the product of pre-fault voltage at that bus. That is voltage of the bus before the occurrence of fault and post-fault current. The fault current after the occurrence of fault. So product of pre-fault voltage and the post-fault current will give the value of short circuit MVA. So now consider the Thevenin equivalent circuit of a power system network. Let the Thevenin equivalent network obtained after solving a power system network be like this. So we have said that after drawing the reactance diagram, we will reduce the reactance diagram with respect to the fault point. And we will calculate the Thevenin equivalent reactance as seen from the fault point. So suppose this is the fault point on a power system network and this is the equivalent Thevenin's network. So we have a Thevenin equivalent impedance ZTH and a Thevenin equivalent voltage ETH. Now fault current is the current flowing to this fault point and it will be equal to voltage by impedance, that is ETH by ZTH, and this pre-fault voltage ETH or Thevenin equivalent voltage ETH can be assumed as 1 angle 0 per unit. And we usually will not consider the resistances of components, so impedance can be replaced as reactance only. So fault current can be written as ETH divided by XTH. And the base current, so while doing ETH by XTH, we are considering ETH in per unit 1 angle 0, and XTH is, we are calculating XTH from the reactance diagram. So in the reactance diagram we will mark all the reactances in per unit. So per unit by per unit we will get the current in per unit. Now in order to calculate the actual current, we have to multiply the per unit current by the base value. And we know the equation for base current. It is MVA base into 10 raised to 3 divided by root 3 into kV base. Okay. So now the actual fault current is per unit current into base current. Now fault MVA. So we have said that MVA is the apparent power, that is voltage into current. Pre-fault voltage into post-fault current. So ETH into IF. So per unit value of IF is ETH by XTH. So this will become ETH square divided by XTH. And as we are considering ETH as 1 angle 0, this can be written as 1 divided by XTH per unit. So fault MVA is equal to 1 divided by XTH per unit. So if we are calculating it in per unit, it will be 1 divided by XTH. And if we have to calculate the actual value of fault MVA, we have to multiply the per unit value by the actual value. So actual fault MVA is equal to, we have to multiply per unit value by the base value. So actual value of fault MVA is equal to per unit value into base MVA. Now always keep in mind that fault MVA is equal to 1 divided by XTH only if the value of ETH is 1 angle 0. There can be certain cases where ETH is having a value other than 1 angle 0. So in that condition we cannot use 1 by XTH. So always remember that the exact equation for fault MVA is ETH square divided by XTH.